first of all, I have to pay the GA. Sorry. So let's see, should we start with questions? All right. Okay, what I'm going to do is try to go over quickly the stuff in chapter 25 that I skipped. Not all of the stuff that I skipped, but some of the stuff that I skipped. The most important of the stuff that I skipped. And then try to get through a lot of chapter 26. It's pretty dense, and I don't think we want to go through it in absolute detail. But let's look at some of the things that I haven't yet done in chapter 25, or have only done tangentially. So you remember we have the big idea was that the covariant derivative was d mu plus an a mu. And let me try to get Schwarz's notation straight here. There are so many notations. In this notation, A is anti-Hermitian, but the question then is, what is it? Is it plus I or minus I and so forth? And, I should have gotten this. Okay, the way Schwarz does it is d mu minus ig a mu ta. Okay, so those are where the TAs, of course, are the generators of the Lie algebra. And in that notation, then F mu nu, which is the commutator of two covariant derivatives, gets multiplied. Schwarz uses an I over G, and then this takes the form d mu a nu. Well, again, I don't know. Yeah, that's right. He uses a mu as, okay. He's writing it this way. He's writing a mu as a mu a ta, and then, gosh, oh, I see. So then he puts in, he doesn't, this is what I do. He puts in an extra, so he writes it this way, minus ig a mu. And so this is minus ig a mu, and then that becomes that. In any event, in this case, this then is d mu a nu minus d nu a mu minus ig a mu a nu. And if you then write this as fa mu nu ta, then the fa mu nu is equal to d mu a nu a minus d nu a mu, and then plus g, whoops, structure constants. F ABC, AB mu, AC nu. For compact groups, whether the color indices are up or down, the flavor indices are up or down, doesn't matter because the structure constants are real and totally anti-symmetric. Okay. And of course, F mu nu is anti-symmetric. It's obviously antisymmetric in mu and nu from this term, which is like the electrodynamical field strength tensor. Here, when you interchange mu and nu, you can fix that by interchanging B and C, and then you get a minus sign from there. So that's why this thing is antisymmetric in mu and nu. You might wonder, where do these structure constants come from? Well, up here, you see this thing is d mu a nu a, well, Ta, minus d nu AA Ta mu, and then there's the term minus Ig, and now we've got Ta Tb AA mu AB nu. And I probably should have done that. If I want to get this, I probably should have done that. BC, BC, and then TB, TC is the minus IG, and this is I, FABC, well, FBCA, TA, I minus I is plus 1, you get a G, FABC. So that's how it works. We all happy, or does somebody want to see something?
So you can permute the indices of the structure constants cyclically. You can permute the...
Yeah, they're invariant under cyclic permutations, yes. And in fact, you can sort of see that because you take the A and you go here, you get a minus 1, and then you get another minus 1. All right, now, I've been talking how covariant derivatives transform under gauge transformations, and the thing basically goes as u d mu u inverse. That's under full gauge transformations. Under infinitesimal gauge transformations, it's useful to write down how A mu transforms. And then you have A prime mu is A mu A plus 1 over G, this is Schwarz's notation, d mu, the alpha parameters, the 8th alpha parameter, minus FABC, the bth alpha parameter, A C mu, and of course the A's are at X also, so something's at X, everything's at X. That's an infinitesimal gauge transformation on the A's, and the F's, which transform covariantly, become F prime A mu nu is FA mu nu minus FABC alpha B, well, let's suppress the X, alpha B FC mu nu. That's under infinitesimal alpha, so alpha is epsilon, which is 4 minus D. That's a joke. So what is the Lagrangian? It's minus a quarter FA mu nu. Well, I don't know why he does that, but he does it. All right, so it looks like that, plus a sum on ij equals 1 to n, psi bar I, delta ij, I d slash plus g AA slash TA ij minus m delta ij psi j. So that's the pure, that's the action density for fermions interacting with the gauge fields. And you can think of this as the classical action, or we can think of it as quantum action, but then typically we'd add, we do the counter, if we're doing perturbation theory, we do the counter term business. There is another term that I should mention to you, and this is an interesting term theoretically. It's called the theta term, obviously, and there's an epsilon, mu, nu, alpha, beta, and what you've got then, at least in Euclidean space, it would be Fa mu nu, Fa alpha beta, and that's then 2 theta. It's actually, it's a total divergence. And I once wrote a paper saying that, well, we can forget this term because for some space-time geometries you can integrate and you get a surface, you obviously get a surface term, but then for some geometries there's no surface, in which case the problem goes away. The problem with this term is that if it exists, this violates CP, and it involves the strong interactions. So you get a big CP violation term. Then the question is, where is it? Because strong interactions don't violate CP. Okay. So, any questions? Pause. All right. We can rewrite the Lagrangian by the action density by expanding the F's, which are this form. And then what we have is L is minus a quarter. And I'm going to use Schwarz's notation now because it's too tiresome to write out all of these Lorentz indices. So when I say square, in Euclidean space it's just a square, but in Minkowski space, obviously you raise, in the second factor you raise the Lorentz indices. And then the other term is the same as we had, psi bar I, and I delta ij, gamma mu d mu plus g gamma mu aa mu taij minus m delta ij psi j. And we're summing over a bunch of indices, the repeated indices. Now, what are the classical equations of motion? When you vary the a mu, you require the action to be stationary. And then what you get is d mu f. I'm going to try to raise these indices on the fly. So fa mu nu plus g fabc ab mu fc mu nu is minus g psi bar I gamma nu taij psi j. And for the Fermi fields, it's I d slash minus m psi I. So this is the kinetic part. That would normally be 0 for a free fermion. And then we get minus g a slash a taij psi j. So these are the classical equations of motion. And Now, this, of course, has local gauge invariance, but it also has global gauge invariance, just when alpha happens to be independent of space-time. And let me repeat one of the nicest pieces of theoretical physics is Nother's theorem, and it's just such a cute thing that I did it last semester, but I'm going to do it again just because I think it's so simple and so important. This action density under a global transformation is invariant, so we get 0 is partial L, partial alpha, where alpha is the either an infinitesimal or a finite but constant global space-time independent transformation. And so what is that? Well, it's, in fact, I can repeat ME's theorem generally. Just suppose, look, the action density depends upon a parameter, but the dependence is trivial. Then we have a conserved current. And the reason for a conserved current when the equations of motion are satisfied. So this is partial L, partial, I'm just calling phi I a field, partial phi I, partial alpha, plus partial L, and of course I'm assuming the action density just depends upon the fields and their first derivatives. Higher derivatives. Partial phi I. Can I write comma mu for the muth derivative of the I field? It just makes things a little bit more compact. And this is partial phi I comma mu partial alpha. So that's the total way in which this thing can depend upon alpha, because L depends upon phi I and the first derivatives of phi. Okay, but now if we assume the classical equations of motions hold, the classical equations of motion, of course, are d mu of partial L partial phi I comma mu equals partial L partial phi I. Okay. And that means then we can replace this term with the muth derivative of the partial of L with respect to the muth derivative of the I field, and then we've got partial I, partial alpha, plus this term. And this whole thing then is d mu of, well, I should have written this down again. So partial L, partial phi I comma mu, partial phi I comma mu, partial alpha. And you notice that this is a derivative of the first term. This is the muth derivative of the second term, because we can interchange partial with respect to mu and partial with respect to alpha. So this thing is d mu of partial I, partial alpha. And so this whole thing then is partial L, partial phi I comma mu, partial phi I comma alpha. So this is the current. The current thing is conserved. And J mu is partial L, partial phi I mu, partial phi partial L. Okay, so that's a very, very general theorem, and it means that every global symmetry of the action density is associated with a current that's conserved when the equations of motion are satisfied. Now, in this particular case, if you take these derivatives of the action density and with respect to the gauge parameter alpha, the global parameter, the global SUN parameter alpha, and also the derivative, the partial of each of the fields. And so you have to consider varying this field and varying that field. You might as well do the infinitesimal transformations, which are these two. And if you keep track of it, in fact, I think I may assign this as a homework. We've got to do some homework in this class. And this is as good as any. So, homework due in a couple of weeks. Derive the following equation, namely that this J A mu is in fact minus psi bar I gamma mu TAIJ psi j plus F ABC AB. Okay, here I've got the problem of what did. All right, I think these are the right indices, but I'm raising them on the fly, whereas Schwartz, for some reason, has everything down, and I don't think that makes any clearer at all, but he does. And so what we have then is a conserved current. 0 is d mu j mu a. In fact, for SU2, we would have 3 conserved currents because of the 3 possible A's. The 3 possible generators of SU2, which typically are the half Pauli matrices. For SU3, there are 8 generators. They're and the matrices are the 8 Gelman matrices, half the 8 Gelman matrices. This thing's called lambda. And what that means is then that there are 8 charges that are actually conserved. And so so the idea is that Q A dot is 0, and the reason for that is this is J d cubed x, J dot 0 A, and then by the conservation law that's d cubed x minus del dot J A. And now, if you integrate that out to a surface of infinity and assume that because of a lack of funding there are no charges on the surface, then you get that this thing is 0. There is something awkward about this, though. This current, it has an A index here, and so you'd think, well, under a global or a gauge transformation, it's not invariant, because, of course, it rotates. So the color charges rotate into each other. So this current is conserved, but it's not invariant under the gauge group, either under the group SUN, either globally or locally. So that's one current. Now there is another current, and the other current is the current that you could make out of the quarks. So let's see, I don't want to use the same letter J, so let me use a capital J. J mu A is minus psi bar I gamma mu TAIJ psi j. What's the story with this one? Well, this one is gauge covariant. That is to say, it transforms in a it rotates, in other words, as the whole SUN. And moreover, it satisfies this equation: d mu j mu a is 0. And in particular, that G, the thing that's 0 is that thing is equal to G mu J A nu. Well, no, mu. Plus G F A B C A. Let me try to get the indices right. Mu B J C I'm running out of indices. Oh, there's an that's in here. Okay. So this thing is, it's the covariant derivative that vanishes. So this current isn't conserved, but it's gauge covariant. This one transforms in a complicated way on the gauge transformations because the F transforms covariantly, but the A's don't. They have the D of alpha, the gradient of alpha. Okay, so that's what's kind of unsatisfying about all these things. Okay. Now you remember that way back when we were talking about path integrals, I did the Fatio-Popov trick. And the deal there is that if you use if you fix the gauge and use a nice propagator, a Lorentz invariant propagator, or in fact, in general, any propagator, you get an extra determinant. You can write that determinant as a path integral over scalar fermion fields. All right. So let's now go then to, let's remember that and now go to the quantum Yang-Mills theory, which is Schwarz's chapter 26. And now I'm going to write then the action density in terms of all of, including the ghost fields. And in fact, for later reference, he actually throws in scalar fields, which would occur in, you could have colored scalar fields in the supersymmetric model, and you do have scalar fields in the standard model of Higgs doublet. And from now on, we're going to have an awful lot of, we're going to have a forest of equations. Okay, and so I'm not going to try to straighten out Schwarz's Lorentz indices. I'll just repeat them the way he does them. Okay, so L is minus a quarter FA mu nu. Of course, you can imagine all this is going to be put in space in case you don't need to straighten that thing. Minus 1 over 2c. Now, here's a gauge fixing term. And then here's a ghost term that, and let me just draw that in order to separate what I'm going to write down now from the rest of it. Then there's a gauge, then here are the ghosts. D mu C bar A, delta AC D mu plus G F A B C A B mu C. So these are colored scalar fields that anti-commute. They don't exist in the initial or final states, so they're called ghosts because you can't detect them, but they're somehow there. Plus, psi bar I, well, this is this thing that I've written so many times already. I d slash plus g a slash a ta ij minus m delta ij psi j. And then here are the scalar fields. Delta ki d mu minus I g a mu. And I'm going to write capital T because the scalar fields could be in a different representation. So I have little ta for the representation of the Fermi fields, and they're typically in the defining representation. The scalar fields typically are also, but not necessarily. So then we have Ta, Ki, Phi I, and then this whole thing, complex conjugated, adjointed, whatever you want. And then the same thing, delta Kj, du minus I, AA, sorry, that's capital A, my chalk slip, so this one's N, underweight A, big TA, AJ, IJ, and then finally minus M squared phi I star phi. All right, and you could have even an I here that have different bases. Although you break the symmetry, so let's give them the symmetry. Okay. Now, let's swing this thing around for a moment, just so I don't have to write it again. The FA mu nu is this. This is the covariant field strength. And if we look at the kinetic terms, or the quadratic action density, LK is just minus a quarter d mu a nu a minus d mu a mu squared minus 1 over 2c d mu a mu squared plus psi bar I d slash minus m psi I minus phi I star. Here we've done integration by parts, so we have box plus m squared phi I, and then we have the action of the ghosts, which is minus c bar a box ca. Where again we've done an integration by parts. So apart from integration by parts, this is the kinetic part, and this is the part then that gives us the propagators. And so if we've got, let us say, nu B, and this is a gluon then, P, mu A, this propagator is I minus, and I'm going to write it as eta mu nu, plus 1 minus c p mu p nu over p squared, and then p squared plus I epsilon, and then this whole thing has a delta AB. And of course, that's because this is just AA squared, basically. It's not AA times an AB. And so that means that, that there's a, the color doesn't change as the propagator goes across. Then there's a ghost propagator. And the ghost propagator Schwartz writes as some dots. And again, B goes to A. along like that with momentum p. Well, this is a particularly simple term, so you get a particularly simple propagator, and it's I delta AB over p squared plus I epsilon. There was no mass term on these Fermi fields. What the hell are they? Up here, no mass term, so the mass isn't there in the propagator. The colored fermions, well, they're just fermions, aren't they? So we just have the Dirac propagator, I, but again, in the kinetic action, there's no change in color. I is a color index here. And so they don't change. And then what we've got is p slash minus m plus I epsilon. And if you're upset with the p slash in the denominator, you can rewrite that as I delta ij over p squared and, p squared minus m squared plus I epsilon, and then you have a p slash plus m up there. So I think I've got the signs right. And then for colored scalars, you've got this J, I, P, this thing, so dash line for colored scalars, p squared minus capital M squared plus I. Okay, so these are all the propagators, and we also have all of these terms, and so we can calculate basically the tree level processes with this stuff. And one of the upsetting things about this whole business is that in QCD, you see you've got 8 gluons, and the action, if we just look at it, you see F has a linear term and a quadratic term. So F squared has a quadratic term, a cubic term, and a quartic term. The quadratic term goes into the propagator, but then you've got an interaction that's a cubic term and a quartic term. And you've got there 8 gluons. And so you've got an awful lot of terms, even at tree level. So in particular, Schwartz writes out the interactions. Again, this is without the counter terms. It's Li is minus G FABC d mu AA nu AB mu AC nu. So that's the cubic term, and notice there's a derivative there because F mu nu has derivatives in it. And the next thing is minus a quarter G squared FE AB A mu A B nu FECD a C mu, that's a mu, a D nu. And then we've got the interaction term for the ghosts, which is plus G at ABC d mu C bar A mu B C C. And then we've got the really important term of the gluon fermion vertex, which is the gauge field psi bar I gamma mu TA Rj psi j. And then we've got the vertex for the scalar fields, and we've got 2 of them. The reason we have 2 of them, you see, is because although the fermion action has this direct form with just derivatives of 1a. Here we've got the covariant derivative squared, which the covariant derivative is linear here. The covariant derivative squared means we've got an a squared term as well as a linear a term. And so these terms are plus I, G, A mu, T A, I J, phi I star, E mu, phi J minus phi J, E mu, phi I star. So those are the terms that are quadratic and phi linear in A. And then we have one that's G squared, phi I star, A mu, T A I K, T B K J, A B mu, I K. So that's the one that's quadratic in A and quadratic in scalar fields. Any questions? I mean, I went to Costco and bought a whole box of new candy on Friday night. And of course, these generators, of course, are commissioned because the group SU is linear, unitary.
I guess I have one. So,
All right, I hear a question coming, so I'm going to get the key. Shit.
alright, so in our middle line, or just the first term in it with the C bar, A and the C.
These are
Yeah,
here.
these guys. So how are we?
How what?
Let's see. So over there, we're just taking it from that, right, and just taking the terms.
Yeah, we're taking, that term that you pointed to came from
D,
here.
C bar A.
D mu,
There's
C
delta.
bar A, G, F A B C,
That's
A
it,
B
yeah,
mu.
okay. Yep. For some reason, I confused myself for a moment. That's good.
There may have been an integration by parts.
Yeah. I think so.
And, of course, if you could do an integration by parts, you could toss out this theta term. All right. Anyway, back at the ranch. So these are the interactions. And so now we can extract the Feynman rules and to have a nice symmetrical convention, Schwartz has all the momentum moving in. And we are going to have vertices that have 3 lines, 4 lines. And so it's good to have a convention of some sort. So if you have nu B, so this is the triple gluon vertex. Nu B, mu A, rho C, P is going this way, K is going that way, Q is going that way. Okay. So this one, and just to define it, it's the very first term. This one is G, F, A, B, C, eta mu nu, this is flat space metric, of course, K minus P rho plus G nu rho, P minus Q mu plus G rho mu, Q minus K nu, big right bracket. So that's the triple gluon vertex. The next, of course, is this one, which of course is ortic gluon vertex, and I'll just write it like this. U A sigma D rho C U B and everything going in. Well, there aren't any momenta, so you don't need to do that. All right, minus I G squared times, and now a lot of terms, F A B E F C D E, and we're summing over E, and it's eta mu rho, eta mu sigma minus eta mu sigma eta mu rho, and then a similar term, F ace F D eta mu nu eta rho sigma minus eta mu sigma eta mu rho, and then finally F aid F C E eta mu nu eta rho sigma. I'm going to fall asleep here. Eta mu rho, eta mu sigma. All right, you can see that this, what we need to do QCD or computer programs, this, doing this by hand is never going to work. All right, I see a question. Yes.
I'm sorry, I don't recall the rule on color for these interactions. These, I mean, yeah.
Here, let me toss you your candy.
So these can, so color can't change on the gluons, and so color is not important for these two.
Well, wait a minute now. We've got here A, B, E, C, D, E summed over E. I mean, it might be a multiple of the identity, but again, it might not be. I'm not sure. I mean, this is...
Okay. I'll look it up.
We'll see in a moment. Then there's a ghost vertex.
I have a question.
Yeah.
What is G mu rho in that bottom equation?
Bottom
What are
equation.
those? Are the what is
C.
G rho mu?
So in the second term, there's a G.
This, oh,
Yeah.
it's supposed to be eta.
Okay, that's
Yeah, I'm sorry. I was copying what Schwartz wrote, but I mean, he likes to use G. I don't know why. Well, it's an English letter instead of the Greek letter, so I suppose it's improved. I owe you a candy.
What is the momentum in that equation? So there's a derivative.
Right, because the triple gluon vertex has a derivative, and the reason is this term here. All right, so when you get your two candies. It's probably fresher than the ones that I was using before, say last week. Okay, here's the ghost vertex, ghost gluon vertex. So there's the gluon, and then here's this ghost coming in and going out. And this is C bar A, P going out, and this thing then is minus G F ABC P mu. Okay, so one momentum. So the ghosts are, you know, might be thought of as rather puzzling things, but their Feynman diagrams are the simplest part of the whole business, which is a good sign because, after all, they're just gauge fixing. Or terms that fix the gauge fixing. Okay, then there's the Fermion Graph, and this one, of course, is the super important one. J I mu color A, and this is I G gamma mu. Oh, I'm using little t's for fermion generators, so TA. So there's that vertex. And then finally there are the scalar vertices. Let me see, the scalars are not all that important. Let me save some blackboard space. I'm going to write the scalar vertices over here. So there are just two of them. One is the gluon comes down. You have J coming in, momentum K, and in this case, he actually has this momentum going back out, Q, I. And so this thing is IG, K mu plus Q mu, and then big TA, J. And then the other one is, which comes from this one times that, times that, times that, times that, times that. That one gives us a 2 gluon vertex, which is, and then, and here's a J, and there's I, and this is a mu B, and this is a mu A, and this is all together I, G squared, big T A, I K, big T B, K J, and then eta. Okay, so these are all of the vertices. Okay. So we must be simply worn out. Now, a lot of this we don't need for the next part of this calculation because what we're going to talk about is the simplest aspect of quark, anti-quark scattering. And so in particular, we can write down the Feynman diagram looks like this. I, P1, P2, J, one gluon exchange, and it's an anti-quark, so K coming in, momentum P3, momentum P4, L, color vertex B, color vertex A. Okay, I think that's everything. So for this one, what we do is we grab basically two of these. And two of these, but we also need a gluon propagator, so we get one of these. And putting it all together with the part of the Feynman diagram, which would be the U bar U and the V bar V for these U bar U up here, V bar V there. What we finally get is that this is equal to, it's lowercase t. You've got to distinguish these generators. So it's TA, JI, TA, KL, and that's because the gluon doesn't change the color. Remember, there's a delta AB there. And then there's an IG squared. Schwartz put an S for strong on the G, but I don't think we need that. And then the top part of the Feynman diagram is U bar J of P2 gamma mu Ui of P1. And then minus I, well, if I had that minus I correctly on this propagator over here. Yeah, it's okay. Yeah, it's just where you put the minus. So you can write it as minus I, eta mu nu minus 1 minus C, K mu over K squared. And the whole thing is over K squared. Well, an extra parenthesis. And then the bottom part is the, you use the antiparticle spin as V bar K of P3 gamma nu V L of P4. And remember, for quarks, or particles as opposed to antiparticles, incoming is U, outgoing is U bar. For antiparticles, incoming is V bar, outgoing is V. All right, so that's it, and of course we can go to some special gauge like Feynman gauge, and we'll do that shortly. But let's first compute some of these things. And in fact, Schwartz considers two examples. In one of them, we've got this incoming one here is red, and this guy here is anti-green. And so what do we get? Well, what we get is TA J1, 1 for red, TA 2L, 2 for green, and if you then look up the lambda matrices and compute these, so that would be a quarter lambda A J1, lambda B 2L. This would turn out to be, these are 3 by 3 matrices, this would turn out to be 0, 0, 0, minus 1, 6, 0, 0, 0, 0, 0, JL, and that's then minus 1, 6, delta J1, delta 2L. So, this guy here has to stay red, this guy has to stay anti-green. And on the, so that's, now of course you've got to consider all the examples and some suitably, but we'll get to that in a minute. Suppose on the other hand that the U was red, but that D bar was anti-red. Well, now what we would have would be TA J1, TA 1 L. And this would turn out to be 1/3, 1/2, 1/2 JL. And again, well, this time they can be different, right? Final state involves red anti-red, blue anti-blue, and green anti-green. So in other words, in the final state, J and the L have to be the same color, but one is color, the other one's anti-color. And so what happens is if you keep all this straight, first of all, there are these rules. You know when you take a, let us say, a spin one, and let's look at SU2. You take a 1/2 and a 1/2 together, you can get a vector, or you can get a scalar. All right. And in the case of SU2, the 2 bar is really equivalent to the 2, equivalent in the mathematical sense. That is to say, the complex conjugate of an SU2 can be written as a similarity transformation on the same SU2 element. But in SU3, they're different. 3 bar and 3 are 2 different representations. And here, what you get is 8 plus 1. So an octet plus a singlet. And by the way, back in the 60s, this is before, obviously, before the internet, but also Xerox machines weren't all that cheap and common either. And this SU3 stuff was all invented at Caltech by Galman and some others. I forget that other guy. Anyway, Sidney Coleman was, I don't know if he was Galman's student or Feynman student, but anyway, he came to Harvard and he knew, he had done his thesis on SU3, so he knew all these relationships. And at cocktail parties, he would challenge people to, he would say, I can do, I can take any direct product and give you the direct sum. And if somebody would challenge him, he'd think for a second and recite it, and everyone was amazed. Okay, what is the singlet? Well, the singlet is 1 over root 3, and it's red bar plus blue bar plus, actually I should have said green bar plus blue bar. So it's RGB is what we normally say. Oh no, he wrote it as PG. Anyway, so that's the singlet. The octets are more complicated. Anyway, if you compute what the effective potential is here, you can imagine this thing looks just like QED apart from all the color stuff. So just as the QED gives you a Coulomb potential, this is also going to give you a Coulomb potential to lowest order, but it's going to give you some color factors. And so if you're talking color singlet, you get a potential V of R. So in other words, if the initial state is a color singlet, the final state is a color singlet, then you get minus 4/3 G squared over 4 pi R for the 1. And if, on the other hand, you have octet in, octet out, what you get is 1/6 G squared over 4 pi R. So this is 8. So this is 1 goes to 1, 8 goes to 8. So what does that tell you? That tells you that the quark anti-quark potential is attractive if the quarks are in the singlet, repulsive if the quarks are in the octet. And this works out very nicely because what it means is that you can expect that there might be in nature quark anti-quark bound states, but not quark bound states. And in fact, we think of the mesons as quark anti-quark bound states. The pion are bound states of U with U bar and D bar and U with D bar and so forth, depending on the charge of the pi meson. And the same thing for the rho and the K, but the Ks have strange quarks in them. And so, okay, so that's that. The next thing then is to consider something a little more general than that, namely E plus E minus goes to hadrons. Hadron, of course, is a Greek root meaning big, heavy, strong. Think sumo wrestler. We're going to be talking about alpha S. This is G squared over 4 pi for SU3. Okay. So suppose we think about this at tree level. Well, and what are we going to compare this to? We're going to compare this to E plus E minus goes to mu plus mu minus. So in other words, I mean, in fact, at the same accelerator, you can be doing final state muons, final state hadrons, take the ratio of total cross sections at some energy, and this is something that is called R. R for ratio. All right. Now, we previously computed E plus E minus goes to mu plus mu minus, and in fact, because the mu's are different from the e's, the calculation was simpler than E plus E minus goes to E plus E minus. And in fact, this cross-section, sigma, E plus E minus goes to mu plus mu minus. What we found was, in the center of mass, it's 4 pi alpha electric squared over 3 E center of mass squared. And we can call this sigma 0. So this is E plus E minus goes to mu plus mu minus. Now, if instead we're doing the quark thing, let's just notice that if we were doing QQ bar goes to, how shall I say? If we were doing E plus E minus goes to mu plus mu minus, we'd have the same thing up here, except we wouldn't have any color factors and we'd have E's here. There wouldn't be any I and J because there wouldn't be any color indices. So in other words, the Feynman diagram is almost the same. The only difference then is that we've got G instead of E, and then we've got these color factors. And what are the color factors? Well, wait a second. I'm being a little bit. Let me just think a second. I think I've skipped something here. Right. Right. When this process occurs, it's E plus E minus goes to QQ bar, and so it looks even more like this. But there's a photon going across, and this, in fact, is the photon propagator. In as much as, I mean, apart from, well, this is the photon propagator. So the diagram here is, well, if it's that, then it's it looks like this if we're going horizontally. So this is U bar U, or U bar, or QQ bar. And then over here, it's E plus, or E minus, actually. So there's a photon across. And so, just as this thing was that, so to lowest order, sigma E plus E minus goes to, let us say, QQ bar. This thing is what? Well, first of all, there are 3 colors. So the cross-section, so there are 3 ways this can happen. And you can imagine if you have a color detector here, you can distinguish them. So we get a factor of 3 for color. We get a sigma 0, that's just the stuff that it has in common. But then the charges are different. The charges here, the electric charges, because we're talking a photon here, the electric charges are 2/3 for the up quark, 1/3 for the down quark. And so what you would have would be to multiply that by 2/3 squared for the up quark, minus 1/3 squared for the down quark, minus 1/3 squared for the strange quark, plus 2/3 squared for the charm quark, where am I? I'm losing track. Yeah, all right, he put these in a very funny order. At the energy we're talking about, there are, of course, 3 ups. There's up, charm, top, down, strange, bottom. Bottoms, so we have 3 of the 1/3 quarks and 3 of the 2/3 quarks, and all the charges are squared. The question then is, what's the energy of the machine? And the energy of the machine, which the measurements that Schwartz is quoting here, the energy was the LEP machine at CERN, which had energies of the order of, well, between 90 and 200 GeV, center of mass energy. And so, what is the ratio? When you put all these things together, and what you get is that R, which is basically just the sum over colors and sum over charges of Q squared, what you get is 3.67. And that's, let's see, did he include the top quark? No, he's only including this is 5 quarks, so leaving out the top quark. The top quark has a mass of something like 100, depending on your renormalization scheme, 160, 180 GeV. And so that was, so 2 of them would be too much. And so this is 5 quarks. However, there's another process here. And the other process is not just a gamma, but you could have a Z0 going across. Because oh, we're out of time. All right, the E plus E, the electron couples to the Z0, and the quarks couple to the Z0. And so when, and it turns out that the charges there, instead of being fractional, are integral, and so R goes up quite a bit. It jumps from 3.67 to 20.09. And so even at tree level, what did one learn? What one learned was that there are 5 quark species, at least at this energy. That was one of the elementary results. And that the charges that people would, well, Gauss originally invented these 2/3 and 1/3, that these were the correct charges, or at least plausible charges. In fact, this tree level computation is good to about better than 4%. I mean, the error's less than 4%. And so this was one of the triumphs. And it wasn't just done at CERN. Before the CERN accelerator, they were doing it at SLAC. And it was just one of the many, many remarkable results that was produced at the SLAC laboratory. That's Fermi laboratory, just far fewer results, much more money, far fewer results. All right, any questions? All right, let's stop.